Hello, everyone. Thank you for joining us today. We have a pretty exciting topic to cover. We will be discussing how to build semantic visual search with ChatGPT and CLIP. So we'll start off with some intros on who's going to be doing the webinar. So we can go to the next slide. So I'm Eric. I'm co-founder and CEO of Encord. I'm joined here today by Frederik. He's our lead machine learning engineer. Frederik holds a PhD in explainable deep learning and generative models and is published in several leading AI and computer vision journals. So we're very happy to have him here today. And the agenda for the webinar will be first to start off talking about why are we discussing search in the first place? Search seems like a topic of yesteryear, and it doesn't seem to be matched with all of the buzz around generative AI that's going on, but I think that's far from the truth. Then we'll go into how legacy semantic search is being done now and basically in the past. And then we'll go over a technical breakdown of searching with CLIP and ChatGPT and some other ideas for enhancing semantic visual search for the next generation. And then we'll cap it off with a Q&A with Frederik and I with some questions that the audience has sent. If you have any questions along the way, please feel free to drop them in the chat and we'll put them in at the end as well. So we'll start with the first question. Why are we talking about search in the first place? And if we see on the next slide, most people, they think of search as a Google search bar or searching in a document. It's not a super exciting or interesting topic to go through. It seems like a fairly solved problem for a lot of the things that we're doing today. But actually, if you think about it, search itself is a form of intelligence. So if we go to the next slide, we can see kind of where it ranks with respect to the other types of AI that people know about. So there's predictive AI, which is what we have before called old school AI, which takes some intention or some objective and translates that objective into inferences and actions. So decisions and predictions over things. And now there's been a rise in the last year or so with generative AI, which takes some intention or some specification and generates newly created data from that. So data that didn't exist before in the world. What search does is it takes some intention and it maps it back to some already existing data in the world. So it is some form of intelligence over a translation layer between what humans or agents want to do and some outcome which is supposed to align with that objective. And the reason that search is really important these days, not just because it falls within this hierarchy of AI, is that it will become very, very important as more and more data is just naturally being generated in the world. So if we go, we can see that with generative AI, as more data is being synthesized and more data is just being naturally created with all the processes that we have, finding the right data becomes a very, very tricky problem. And so it becomes important for us to come up with the new methodologies and use some of the creative ways that predictive and generative AI are moving into for the purpose of search. What search does is that it's the first layer of organizing and understanding your data. So again, mapping from intention to some already existing data that exists in the world. And while some of the old methods have done pretty well up until now, there are likely to be limitations as the generative AI boom takes off, and it'll be harder and harder to find interesting things that you want to see within existing data sets. So we'll start off with going how legacy search has been built up until now, and I'll pass it over to Frederik to go over some of the existing methods and then how we're looking at it using some of the new methods, including ChatGPT and CLIP with search with visual data. So I'll hand it over to you, Frederik.
Right, thank you. Yeah, so before I get my hands too deep in the dirt, let's just pause for a second. I'm going to give you guys like 20 seconds, 10 seconds maybe, to think about what is the difference between structured and unstructured data. Right. So you probably came up with some sort of an answer from your, I don't know, system one, a quick response. I like to think about it this way. So structured data is all the data that you can put into tables, and you can give the table columns proper names. And then afterwards, you can search your tables based on these columns or these properties in each of the columns. And unstructured data, on the other hand, is all this data where you don't know exactly what's there. You know that there is a lot of stuff, and there's a lot of stuff you want to find, but you don't have a structured way of sort of attacking the problem. And so why is this interesting? And the reason why it's interesting is because this is sort of where visual semantic searching, it came from. So I thought to myself, if I want to talk about visual search, where's a good place to start if I want to figure out what is the things that were done before all this generative AI hype? So a good question to ask is, of course, what did Google do? And if you look at some of the things that Google did and did really, really well, it's first of all cataloging a lot of data into structure. So that is basically the table on the left, right? So if you have a big table and you know, for example, for images, what the images are, perhaps you know stuff about their location, at the time the image was taken, that tells you something about the time of year, right, for example. And you may also know additional things like tags, or you might have other sources of information. Then putting them into a table makes it very easy to define very specific queries to get very specific data. And so this is sort of the first step. Another trick that Google employed quite a lot is the internet. And so the internet is full of HTML, and HTML is to some extent well-defined. And for example, you have images in a well-defined structure where you sort of have a file name, and you probably have like an alt text describing what the image is. So already here you have some, like if you're a machine learning engineer, right, you already have some sort of label for your data. You might also find a caption, or you might even find, you know, surrounding text that somehow indicate what's on the image. And then to take it one step further, what was also done before all these big deep learning models was a lot of heuristics around figuring out what the content of images are. So for example, a lot of the work prior to all these models was revolving around color histograms. So typically similar images have similar color histograms, right? It revolved around trying to figure out what are the shapes of the objects in the images. You can do that by like very old algorithms for detecting edges, for detecting these sort of what's traditionally called superpixels, that are sort of blobs within the image that have similar content. And then you can construct another of these structured databases over all this information, the color histogram, the shapes of the data, and perhaps you can even take it a step further and do something like SIFT, which is this feature extraction algorithm that basically finds key points that you can match between images. And even if the images are rotated, or the brightness changes, or the hue or the saturation, these kind of things, they change, then you will still be able to do some sort of similarity search and find similar images. So these are sort of all some of all the things that were done previously. And it gives a good insight into what the big problem is, right? We have no idea about what's the semantic content of the images. We only know what are the features of the images. So we know, perhaps we know the shapes and the colors and stuff like that, but we don't know, like a cow is a cow or a cat is a cat, right? We know only these sort of low-level features. So this is really where these new models, they open up for a lot of very, very interesting and cool use cases. So let me sort of open that book and tell you a bit about what we plan to cover today. So two of these models that are sort of very hyped and very useful in the context of visual searching. It's the CLIP model and the ChatGPT model. And the CLIP model is basically a deep learning model that has a very good semantic understanding of the content of images and also of text. So you can both show it text and images, and it knows basically what it means when you show it either of these. So this allows what we like to call direct semantic queries. And that is, for example, I want to find cats and dogs close to trees within my data set. And then, as I'll show you in a minute, there's a way where you can actually use CLIP to try to identify exactly these images in your data set. The other very hyped and very popular model is ChatGPT, right? You probably, all of you tried using ChatGPT already, so you probably had a conversation or more with the model. So it's this text in, text out model where you can prompt it with questions or like exercises or puzzles or whatever you want, and then you will get a textual answer in return. So this model, it lends itself nicely to what we like to call indirect semantic queries. So you can basically turn unstructured text, so that could be anything you are searching for with natural language, into something structured that we can use to query structured data. And that takes away this annoying thing that up until recently, you needed to know some sort of programming in order to be able to at least efficiently interact with all these structured data tables. So you can now get rid of this with ChatGPT. So this could be queries like bright images with many objects. So if you know if an image is bright in advance, if you know that how many objects there are in the image, then you can just take this query and then translate it into something that the computer will understand, and you can precisely filter your data. So this is basically the idea for today, is trying to cover these two different approaches. Right. And so let me give you sort of a slightly better intuition for what happens when you use the CLIP model. So the CLIP model is this big neural network that has two components. It has an image understanding component and it has a text understanding component. And so if you pass an image to CLIP, what it'll do is it'll basically take this image and generate a point in a coordinate system like this. And then you can do this with a lot of different images. So here's a bus, right? I can show it to CLIP and it'll tell me this is the coordinate for that bus. I can do it again. Here's an elephant. It'll be somewhere else in the coordinate system. And then the very cool thing is that if I now show it a second bus, then when I ask CLIP to put this one on the coordinate system, it'll very often end up in the very close to other buses in my data set. So already here, right, this is very, very useful. So now I could, if I had, let's say that this second bus was my query. So I wanna, it's not quite natural language yet, but we'll get there. If I had a bus and I tried to find more buses in my data set, I could just show CLIP this new bus that I'm using as my query. And then I could go over to the coordinate system and find all the other ones that are close to that point in the coordinate system. So this is one way I can sort of do visual queries. But the other component, as I mentioned, is the text component. So I could also have a query like serve, which is this plain text. And now, because CLIP was sort of, it basically saw, you can think of seeing the entire internet of images and captions. And then it learned to align these two things. Then when I show it this query, it'll also put that into the coordinate system. And now I can do the same trick. So I can do this sort of a neighborhood search for data, and then I should find images of something related to surf. So this is this direct type of visual querying. Right. And the second thing is ChatGPT. So now we are in this domain where we have text in, text out. So that means that we need to be a bit more careful about how we use the model. And typically, if you want ChatGPT to help you do something very structured, a good baseline setup is something like the following. So you start by telling ChatGPT what type of agent it is. This could be, in our case, you are a data specialist that needs to help me find all the relevant items in this table according to a query. And then the next thing you do is you give it a context. You say, so the context is the data frame, or the table I have looks like this. And I want you to translate my query into something that can, select something from that data frame or that data table. And then you can specify some rules. You're not allowed to, select more than 10% of the data. I expect you, if you don't understand the query, please tell me instead of, hallucinating. Basically, sometimes you see these models like making up things that doesn't exist. So this is sort of a shortcut to avoid that. And you can tell it the expected output. We'll see a very smart way of doing that in a bit. So you basically say, I expect you to tell me the result in this particular format. And then finally, you give it the query I'm looking for is images with high brightness and your query. Right. So this is sort of the high level. And now let's go into more details. So this is where the demo starts. And what we will cover is basically trying to build a visual search system with these two different models. We will do direct search with the CLIP, as I explained, and we'll do indirect search with ChatGPT. And then the idea is for this demo to combine the two in such a way that we first find the, let's say, top 10% most relevant images. And then next we will refine the result even more by doing an indirect search. Okay, and then I'll show you how we've approached it in our product shortly as well. Right. Okay, so this is the setup roughly as I described it. We will be installing Encord Active. It has many of the dependencies that we will need for this demo. And we'll also be installing the OpenAI module and LangChain, which is a very convenient tool for operating with these large language models. Then the idea is that we will have a bunch of images and we will have some queries. We'll have a direct query, for example, people doing sports. And then we'll find the directly relevant images from this data set. And then afterwards, we will query ChatGPT. Could you, on this subset of data, could you find all the bright images with many objects, for example? So this is this indirect query. Okay, and then hopefully what we'll get in the end is some very relevant images for what we are looking for. Okay, so let's start with CLIP. So what we're aiming for is something similar to this. So we want to import CLIP, and we might want to import Torch as well. This is one of these deep learning libraries. It's especially the one that is used for implementing CLIP. This is not something we did. This is something that is open source from OpenAI. And then we want to somehow load our images from our data set, and we want to load the model. And CLIP has a bunch of different models. We're just going to use one of them. And then finally want to embed the images. This is basically the exercise that I showed you before, where we say, this image, could you please put it on the coordinate system? We want to do that for all the images. And then we want to do some similarity search. So we want to specify a query, and then we want to search them. All right, that's the idea. And so one thing I want to mention before I show you the actual code is that you're going to see a bunch of these plots here, and I've showed it in 2D already, but in reality, it's a high dimensional thing. So it is actually like a coordinate of 512 points, not just 2. But we get around that with different sort of dimensionality reduction methods. And so what we want to be able to find is something like this guy surfing, right? And we want to know how similar this point is, or this image is, to our query. Okay, so let's jump to a notebook. Uh-oh. Okay, let's hope the demo gods are with us today. So the first thing you will need to do is you will need to install Encord Active, and it might take a minute or two. So I might just start slowly with, oh, well, was that it? Was that it? Let's see. Okay, I might as well just start slowly with the code. So okay, it's not looking as I'm used to. So the first thing we do is, of course, load the data, and I'll download the Coco validation set from from Encord Active. It's very convenient, very easy to do. And then we will do some imports, not really interesting as well. We will load the project. So now here in my directory, I should have this open source Coco validation project. And I can load that in to the memory. And now I want to build a data set. So what I'm going to do is I'm going to construct a pydantic model of my dataset images. So it's going to have a path to the image, and it's going to have a data hash, which basically links the image to the Encord project. Okay, then I'm going to instantiate an iterator and then just grab all the images. Nothing fancy here. So it's just a list of images, image and data hash pairs. Right, so we can see it here. It's just this list, nothing interesting. And so now here we come to the CLIP model. So the first thing you will do is you will load the model. And that is fortunately very, very simple with this open source code. You import CLIP and then you do clip.load, and then you tell it what model you want to use. If you want to do it on the CPU, on the GPU. And that's basically it. If you haven't downloaded it already, it'll cache the model weights and it'll just load it. Now, the next thing that happens is this embedding of images. So this is just a function that defines how to take the CLIP model. Uh-oh. What did I miss up here? Oh, I actually need to run this. Okay, there we go. Okay, so we just take the CLIP model and a list of images. And then basically what it does is that it'll batch the images in batches of 100 samples per batch. Then it'll compute these embeddings and store them in an output variable, concatenate them in the end, and that's basically it. So here we can see the inference speed. So if I take 1,000 images, I can embed them on the GPU. And I think it's probably a V100, NVIDIA V100 GPU. So I typically get around 60 to 70 frames per second on this data set. And I'm pretty sure that the GPU is not completely utilized. If you had an A100, I think it's roughly a factor 3 faster. And so, okay, well, slightly less in this case. Right, okay, so now we have the embeddings. They are in this big table. So now what we want to do is we want to be able to search them, right? But before doing that, I'm just going to show you how to do this 2D embedding. So if I had I plotted the this embeddings shape here, we would have seen these 512 dimensions. But now we can do this trick where we use UMap, which is a nonlinear embedding method that'll basically take these high dimensional vectors and put them into a 2D space or 2D coordinate system, where similar vectors in this high dimensional space that we can't really visualize, they will be likely to be close to each other in the 2D space as well. Okay, so this is sort of our base for doing the direct search. Now, the next thing that is sensible is to build some sort of index, so some sort of search structure where we can search fast. And fortunately, Facebook AI, they have made a very cool library for that. It's already installed on these Google Colabs, where you can just provide a list of embeddings and then you can query them very efficiently. Okay, so I've built an index. I've added the embeddings to the index. So this is basically my search engine, the index. And now what we want to do is we want to try first the image search. So I showed you that you can take a bus and try to search for similar buses in the dataset. This is what we're going to do in this particular code cell. We take a random sample from all the images that we didn't put in the embeddings. So I actually didn't really cover that, but I basically split all the images from the project into two, just to sort of illustrate that you can do this similarity search also with images not within the dataset. And so we grab a set of random images from that pile, and then we will compute the embeddings. These are the images, and here we can call the same function again, embed the query images, and then we can do index.search on these images. And if we do this little normalization trick here and up here, then this thing basically becomes cosine similarity. So it's basically just normalizing every vector to its unit norm, if that makes sense too. Else it doesn't matter. Okay, so now the last part is just the plotting. Let's see how it looks. So actually the main time for executing this cell is just plotting, and we'll see that a bunch of times. It's a pretty big plot, and it takes a bit to run that on the CPU. See if it works. There we go. Okay, so what we see here is this 2D embedding space that we computed. The red point is the query image in the embedding space, and the orange points are the excuse me, the nearest neighbors in the high dimensional space. Okay, so they don't necessarily correspond. We can see that in the second row in a bit. So the query image is this image of, I suppose, one guy, but multiple instances skating, and we'll find a bunch of other images of people skating. For this second image, we can see that in the 2D embedding space, the actual query results, the nearest neighbors, they're far away in the embedding space. So this is one of these things that sort of come from this transform from a high dimensional space to a low dimensional space, that you cannot represent everything you can in a high dimensions in low dimensions as well. And we can also see that the result is not that great in some sense for the second one. Like, it's also a hard one, right? You're looking for something pretty undefined, and then you'll also get something less defined, I suppose. Same goes for, like, you can query for computers, and you will find more computers. You can query for this red thing with fruit, and you will find red things and fruits. So this is sort of the image search, but it becomes a bit more interesting if we do the same thing for text. So the code is basically the same as above, but now we just replace the sampling of images with these couple of queries. So I would like to find some surfing, some motorbikes, transportation, and maybe some red flowers in a vase to get a bit more specific. So I knew I had that up here, right? So I was just trying to see if I could actually find that. So let's see. Again, the code is relatively simple. So we have to tokenize the strings. That is basically taking each of these strings and clipping them up into separate tokens. That could be red and flower and in and a and vase. Then we compute the embeddings, and we do the search. So same thing, ask for a coordinate via CLIP, and then look for the nearest neighbors in this coordinate space. Cool. So it seems like it's finding surfing. And one thing to note here is the similarity scores. They're way less than they are for visual searching, or like for searching with images. So now I use this information to sort of eyeball in a hyperparameter in a bit. So it seems like most of these similarities, they are in like 2.8, 2.9, 2.6. And if I search for transportation, well, an elephant is transportation, I suppose, but it seems like this is sort of close to the threshold where I probably don't want the results. So I use roughly this number to threshold things later. And it did actually find the red. red flowers in the vase. Okay, so let's get back to the slides for a bit. This sort of concludes the first part, which is the CLIP search. And we're going to share the notebook afterwards, so you will be able to just rerun everything if you want. So no need to take a lot of notes there. Right. So let's jump to ChatGPT as well. So here it would be really nice to be able to say, oh, let's get a model. Let's write this indirect query. I want bright images with many objects, and then let's just load the data and let's see the results. So we would be hoping for something like this, right? If we're looking for brightness and object count, then we would like to see something like this. So very bright images with a lot of objects in them. And again, this is text in, text out. So that we have to follow this process of sort of defining the context and the rules and the output format. And then we need to afterwards provide the query. So let's see how we do that. Here, I first load a data frame from the project that I downloaded from Encord. So Encord Active has this building block called quality metrics. Quality metrics are basically any predicates you can attach to your data. So that could be the object count or the aspect ratio, the contrast of the image, all the things that you can sort of compute around your images or your videos or your labels. And here we have them in one giant table. And so, for example, we know how blue an image is. We know the aspect ratio. We know the area and how red it is. All these kind of things. And the idea for this demo is basically to take this and ask ChatGPT to help us filter it based on these semantic queries. So the first thing you need to do when you work with OpenAI, oh, it feels like it has an answer from me already here. I don't think it's correct, but I do have it here. So we need to provide an API key. I'm not going to show you that one. And then afterwards, we can start setting up the thing. So the first thing we're going to do is we're going to try to define all these rules and set up the context for ChatGPT. So first thing we're going to do is we're going to let the system tell ChatGPT what type of assistant it's going to be. So you're going to be a helpful assistant that translates human queries to filters that apply to a data frame. All right. And then the next thing we're going to do is we're going to provide some instructions for ChatGPT. So columns in the data frame, they are these columns. It's all the columns that I showed you up here. And here is the data frame description. That is actually exactly this description. So in this description, ChatGPT will be able to see that for blue values, the mean value is this, the standard deviation is that, the minimum value is this, the maximum is that, and here are the quartiles as well. So it'll have some sort of summary statistics of all the columns we have in the data frame. And now we also want to provide a bunch of rules. So for example, sometimes queries can be a bit ambiguous. And so we just say the top, highest, and largest means the highest quartile, just to make it a bit more, the task a bit more specific. Same goes for low and bottom and least. And then we want to say that this minimum value and the maximum values, they need to be numbers. We want to say that the minimum value should be smaller than the maximum value. And then finally, we want to give this opt-out option. So we want to say that if you're not able to answer, then please respond with this particular answer. So this basically says the column should be unknown and the value should be something that we don't care about. Okay, so that's the setup. And now one thing we will do is we will say, please answer this user query. And then we will put in some format instructions. And this is, when I discovered this, I got so amazed. So I hope you will be as well. So we'll cover that in a bit, these format instructions. But it's basically telling how should your output look like. So text in, text out. So this is a template. And now the output we can define in Pydantic models. So if you've been developing in Python, you've probably seen Pydantic models already. So it's basically a way of specifying how you expect your data to be. So in this case, I expect a filter to be a string. that represents the column that I want to filter. I represent the min value as a float and the max value as a float. So basically the idea is that I want ChatGPT to pass me a list of filters that I need to apply to my data frame to get the relevant data. So I can do that, and I can formulate a couple of checks that I want to make sure. So if the column is unknown, it's fine. Otherwise, I want it to be in my data frame because I can't filter on a column that I don't know. I want the min and the maximum value to be numbers. I want the minimum value to be smaller than the maximum value, all these kind of things. And with this model, so this is sort of the definition of what I want. I can construct a pedantic output parser. And this is really where the magic happens. So I don't need to tell explicitly ChatGPT how I want the output to be, because this parser is going to do it for me. So I can just say get format instructions from the parser, and then it'll actually provide all the necessary details. And someone much smarter than me probably spend a lot of time optimizing this thing. So this is basically what ChatGPT will see. It'll see all the stuff that I sort of covered, that you are this kind of assistant, you have these columns, this data frame, these summaries, and somewhere down here, there will also be a schema for how it's expected to respond. It's kind of hard to comprehend here, but it's just really cool that this was automatically generated. And so now what I can do is I can take this parser, I can take the prompt, and then I can basically get that string from the prompt, and then I can pass it to ChatGPT and ask it for an output. Another really cool thing that you can do with it's from LangChain, so it's with these this large language model library, is that you can just say, oh, let's try to do a retry if it fails the first time. So I'll just say I want the same parser, and just so this thing will just say bring it back to ChatGPT, say, oh, it failed the last time you responded this, could you try to fix it, basically. And then it'll try again. So here is my prompt. And now let's see what happens, see if it still works. This is one of the places where I cross my fingers and pray to the demo gods. Yeah, there we go. So for this query, what are all the images with both high contrast and many objects? I get a list of filters where it filters on contrast, where the minimum value should be something and maximum should be something above that. And the object count should be probably in the top quartile. So that's great. Now let's just have a look at how it looks, see if it actually makes sense also visually. Yeah, seems so. So high contrast and many objects seems to be true. So one thing to note is that we got like 351 results, and this plot is sorted by contrast. So you will see those with the highest contrast within the data set. Great. So this is a way of doing indirect search. And now skipping back here really quick. Now, of course, it's wedding time. So we want to be able to stitch these two things together. And in the interest of time, I'm going to do this relatively quick. So the idea is exactly the same. As I presented previously, we embed the data set. This might take a while. Now it's like 5,000 instead of 10,000 images, so it should take slightly longer. Then afterwards, we define a couple of direct and indirect queries. So first of all, I want to find outdoor sports where all the images with high brightness and many objects are filtered out. Then secondly, I want to find transportation, and I want to find all the objects with the high annotation quality. Okay, let's run that next. Then we do the similarity search with CLIP. And then finally, we do a filter based on this similarity search on CLIP and take that data frame and then further refine it with this indirect query by ChatGPT. And then we can plot it. So let's see this. Okay. So maybe we can come back to that. So what I wanted to do as well was show you how we did it in Encord Active. So let me start with this open source validation COCO dataset. So what we have done is that we have included both these 2D embeddings that I described from UMap, where you can sort of filter your data based on these embeddings, like this. You can also do the, okay, I suppose I didn't enable it. So the image query search I showed you, you are also able to do if you click this button, but it's disabled. Then they struck me, the demo gods. Finally, it was bound to happen, I suppose. Right, but you can also do these text queries. So if I want to find all the transportation stuff, then I can just hit transportation here, and let's see. Then it should find me all the transportation images. Or if I want to find, maybe I can find this red vase with flowers, or was it red flowers with a wet vase? Okay, well, there we go. I can also do the other thing we talked about with ChatGPT. So I can search for very right images, and I have this available all right at the tip of my fingers. And so we think this is really, really powerful in terms of querying your data based on visual content. And one more thing I want to show you is if I jump to this other data set, they're also doing similar things for the model performance. So you can see here, for example, that you can, so this is a classification problem. It's Caltech 101. This is the test set. There's a lot of stuff here. I don't want to go into the details, but what I want to show you is this thing in the bottom where you can do queries on your model performance. So you can say, what are the top 3 performing classes in terms of mean prediction, for example. And then what you will get is that you'll basically get the response from ChatGPT. Yeah, I wanted to show you one more thing here. So let's just try another one. So how well is the model performance in pizzas, on pizzas in terms of correct classifications? And then you'll get the code to compute that, and you'll get the score in the end. So these are some of the things that we have been building into Encord Active. And so we want to make sure that everyone avoids building these large data, notebooks just to do search on their projects, but instead are able to do it right away. And so here are the results from combining the two. So now we get, for example, if we search for outdoor sports and we search for all the images with high brightness and many objects, then this is what we get. So high brightness, many objects, seems like a lot of outdoor sports. Also a couple of false positives here, I suppose. Yeah, but this is basically a matter of fine-tuning. And when I say fine-tuning, I mean it in like a broad sense. So you could fine-tune the models, but you could also fine-tune hyperparameters. There's something I haven't showed you for these large language models, which is few-shot learning as well. So in summary, CLIP is really good for these direct semantic searching queries, and it's extremely easy to use. I hope that was clear from the demo. It's not using CLIP that's hard. It's basically all the other stuff around plotting and these kind of things. Then, as I mentioned, CLIP has been basically trained on the internet. So common images with common descriptions, they're easy to find. But we have seen for some of our projects that for more specific data, it becomes slightly harder to find these things. And that sort of hints at we need to figure out how to improve these models, for example, CLIP. And one of the approaches here could be fine-tuning. And one of the things you can tune already is the similarity threshold, of course. I didn't really cover that much, but you could definitely set that higher if you want to be more accurate. Then you might leave stuff out as well. On the ChatGPT side, it's really good for these indirect semantic searching queries. It needs a very well-defined task. It might have looked simple, but it takes a couple of iterations before you get it right. Sometimes the context can be too large, and the context is basically how much information you give the model when you query something. So if you show too many statistics and too much stuff before actually giving the query, it might get confused. So these are some of the things you need to sort of take care of. Then finally, you can do even more prompt engineering, right, to tune the performance, but you can also do stuff like few shot learning. So you could give it a list of examples and return like outputs that you find good, and that will should improve the model quite a bit. And then, yeah, so that's few shot learning. And then of course you can also fine tune as well. Yeah, and then, I suppose I could do this. Finally, I just wanted to mention that we'll share these slides, and there are a couple of resources here. So we have the Colab notebook, of course, and then there are links to the CLIP paper and the repository, link to ChatGPT. Then we also tried employing ChatGPT as an ML engineer for a day at some point, and there's a blog post about that. And finally, we also have a deeper dive into what this similarity search with the CLIP actually is. So just a couple of notes there. And then, yeah, I think I'll pass it back to you, Eric, for the last bit of the webinar.
Yeah, thanks a lot, Frederik. That was really interesting going through all the different work that the team has done. I also wanted to give a quick shameless plug on who Encord is. So we are a data-centric platform for computer vision, and we work with AI companies, groups, and individuals and help them create, manage, and validate their data and models. And we have two main components of the platform. There's the Encord annotation platform, which helps people annotate data at scale, and then Encord Active, which is a lot of what we covered in the webinar today, and where we're putting a lot of research into these different search modules, different ways of interacting with these large foundation models, both on the visual side and also on the side of generative AI. So Encord Active is open source. You can pip install it today. If you have any questions on any of the tools or things that you found in the webinar, please feel free to reach out. So enough of the plug, and we can get to the questions, because there's been quite a few both sent in before and a few in the chat as well, which I wanted to give some space to cover. So I'll go through some of the questions that I haven't answered just as we've been going through the webinar. And the first one that came out was, how does this work for images with more complex scenes where there are multiple different objects? I think you're on mute now.
Sorry. Yeah, I think that's a really good question. Generally speaking, the simpler the image, the better the performance, I would say. So for very complex images, one of the tricks that you could employ is that you could do some sort of cropping of the images. So basically make a sliding window and then ask CLIP for each of these windows, what do you see? So that would give you sort of a way of making complex images more simple. Yeah.
Yeah, one of the things that we've been doing a lot of, and the reason why we're showing two different approaches, is the combination of approaches together really is the way to handle complexity, because just tackling it with a naive approach won't work for things which are slightly more complex. But if you think about the problem space and you use all the tools at your disposal, it actually can work for some of the more complex scenery that we've seen, both this indirect and direct methods, as well as some other tricks and things that we've been thinking about. So one of the questions here, how are the objects in the images segmented? I don't know if this is some of the images that you were showing before, Frederik. I could probably answer some of that. They were probably segmented with the Encord annotation platform, which read the labels and segmentations directly. Otherwise, I think a lot of this was open source data sets where the segmentations and labels were already produced. Would it be possible to fine-tune the embedding space of CLIP for a domain-specific use case? How much data would be needed?
Yeah, definitely. So the way CLIP works is that it has this objective of aligning text and images in this like coordinate system, basically. And if you have data where you also have some sort of metadata around your images, then you can definitely do it. how much data is necessary is not one answer fits all question, I think. But what we have seen is that you typically don't need that much data. Like in the order of thousands is typically very good to get started. And yeah, but of course, like the further away the data is from what's on the web, the harder it becomes, and the more the data you most likely need.
Yeah, so that leads to the next question. How does this approach work for radiographic images? What model is used for embeddings? We have actually tried this on different types of medical images and various modalities. It actually works fairly well, surprisingly. Some of the search methods, especially some of the indirect methods based off of metrics which are computed from the library of quality metrics that are in Encord Active. The embedding model is CLIP that we're using kind of off the shelf, which can be fine-tuned as stated in the previous question. But some of the, you'd be surprised how many images end up in the internet, which this model, these types of large models just implicitly train on. So what we found is, surprisingly good results, but for any specific use case, tuning is probably prudent.
And so maybe to add a bit of context, sorry, there are different components, right? So one is just searching more images based on an image. For that part, it works extremely well. And if you want to do a text query, like a direct text query, that's where you might need some more, adjustments and some more efforts. Yeah, and of course the indirect, if you have, as you said.
Are you using SAM within your annotation platform? Yes, so that's an easy question. I think we were the first platform to get SAM out. We worked over the weekend to integrate it. Once the paper came out, we saw how powerful it was, and we put it in, and a lot of our customers are currently using it to great effect. Some of the questions that were also sent in beforehand would be interested to know more about data privacy concerns in conjunction with this technology, especially with respect to GDPR and HIPAA.
Yeah, that's also a really good question. So obviously, also Encord, we really care about security and privacy. And so if we maybe just forget about ChatGPT for a bit, then CLIP, for example, is an open source tool, and you can run everything like in your own secure environment, and nothing there should have any issues. And when you think about ChatGPT, on the other hand, there are many open source models or competitors that basically does roughly this as good a job as ChatGPT. So I don't think it's going to be a big hassle to obtain the same thing, but without having to give anything away to OpenAI. So yeah.
That brings it to, there's another question that came in, which is very much related to this. What are your recommendations for open source LLMs that could be used to replace ChatGPT locally for these tasks? Do you have any specific ones that come to mind?
Well, not at first, no. I think a really good place to keep an eye on this is Alpha Signal, actually. So now this is another plug for something that I'm not associated with. But they have these weekly newsletters, and basically every week there's a new model. That's why I can't remember one name, because there's basically a new model every week that beats all the other models in something. So it's a good place to keep an eye on.
Cool. I'm interested in how this could be applied to real world videos and not just images to summarize scenes in videos or aid navigation in videos.
Yeah. So what we do with Encord Active already is that we do this analysis that I just showed, or we just showed, on the entire video. So you can still do all the same things, but of course, if you have terabytes and terabytes of video, you might need to, be a bit more careful about how you do it. So for example, it might not be necessary to sample every frame. You could probably get a factor 10 or 20 pretty easily there, right? And some of the quality metrics, they're still very fast to query. So the indirect way of searching would still work very well, but I think some of the things related to videos might be slightly harder. And there are also other tricks you can employ. So for example, just looking at FFmpeg, for example, you can find where frames changes like rapidly. So you could start there, right, and look on both sides of that change. Then you could detect changes as a quality metric, and then you could search afterwards.
Yeah, and some of these quality metrics are already natively calculated. Maybe 2 more questions, and then we'll wrap it up. So how to adapt the semantic search using CLIP plus ChatGPT for custom domains like industrial inspection. So we talked a little about fine-tuning. Any other kinds of adaptations that you can think for this?
I think this is maybe a good place to, like we've been mentioning a couple of times, these quality metrics. So probably for these kind of use cases, it would make a lot of sense to think about what is it exactly that I'm looking for. And typically you can define that in a simple piece of code, and then you can actually translate that into a quality metric. So for example, let's say you have a reference image and you're looking at whether there's a defect, right? So you can probably compare this new image to the reference image, and you could do that with a simple piece of Python code. And then you could give it a score, and then you already have sort of the grounds for searching your data. So that might make it a bit more clear what these quality metrics can do. So we like to think about them as every predicate you can put on your data, basically. And this is one of these places. Unfortunately, it's really easy with Encord Active to define these small functions and then have Encord Active take care of the rest.
Yeah, they're customizable for arbitrary use cases. All right, last question. It kind of wraps up a few of the other questions that are stated as well. Considering the increasing scale and complexity of visual and textual data, what approaches or strategies do you foresee as crucial for ensuring the scalability and efficiency of a semantic visual search system powered by CLIP and ChatGPT?
Yeah, another really, really good question. So scale is definitely something that we think a lot about. And obviously some of these things that I've shown today, they're not scalable. So if you want to load everything into memory, that's definitely not something you want to do if you really want to scale. So you want to be able to define data structures and databases in such a way where you can query very efficiently based on these different things. And I think one of the things that would be really good to do is swapping the order of what I showed today. So you probably want to do the indirect search first, because you can do that on databases, and databases are really, really fast. And the second thing is that then when you do the search on these embeddings, there are some very, very powerful libraries for doing that. And they can, okay, how to put it easy. So there are many tricks where you can actually employ tiny AIs to tell you where to look to avoid looking through all the data, for example. And there are many of these sort of tricks you can do to scale very efficiently. But it will become a trade-off between like accuracy and performance. That's for sure.
Great. Thanks, Frederik, for the presentation and for all the demos. Again, we'll share the notebooks after the webinar is ended. And we'll wrap it up here. Thank you, everyone, for joining today. Please feel free to reach out to me or Frederik directly, and be on the lookout for future webinars. We have some other pretty exciting topics in store. So have a great rest of the day, and we'll be in touch.